Hey everyone, here is the warm-ups for our second lesson in Unit 4. So let's go ahead and take a look at these before we actually get into the lesson. Number one, it says to identify the extreme values of the graph. So I'm going to go ahead and graph this function up here so I have something to refer to. We have the graph of a function. We could call it f or g or something like this. We have a as an endpoint, or x is the a equals x is an endpoint, and at b you have an open circle from the left and then a closed circle from the right, and then it kind of dips down and then comes back up and then goes back down with an open circle there. This endpoint here is at d. This point here is at c. And so there's the graph, and we're looking to identify the extreme values of the graph. So in the first lesson we talked about the idea of extreme values, and there are relative extrema and there are absolute extrema. So absolute extrema are the highest point on the graph period or the lowest point on the graph period, where relative or local extrema are the high points within a very small window or the low points within a very small window. So let's go ahead and get started, and looking at each one of these points here, each one of these x values, let's figure out what we have. So if we look at x equals a, if we look within a very small window around a, we can see that there is no higher point than the y value when x equals a. So we would say that that there is a relative or local maximum when x equals a. We would also say that at b, even though it's a discontinuity, we have a jump discontinuity here, if we're looking at the point b, if we look at points just to the left and just to the right, we notice that the value that we get when we plug in b is higher than any point that's immediately around it. So if we just move to the left, we can see that it's higher than all those points. And if we just move just to the right a little bit, we can see it's higher than all those points. So we can say that there's a relative max when x equals a and x equals b. We can also say that at c we have a relative maximum. Now we could go further with that one, but we notice that at x equals c, that every point around it is lower than it. So we have a relative maximum when x equals c. Okay, now let's go ahead and talk about relative minimums. Well, let's see. Relative minimums occur when that point is lower than any point that's immediately around it. So we've already said that when x equals b, there's a relative maximum. This graph should be bottoming out here at 0, at x equals 0. My graph's a little off here. But we could say here at 0 that that is a low point in comparison to the points that are immediately around it. Again, if you look just to the left and just to the right, we notice that f of 0 is lower or is less than any points that are immediately around it. So we have a relative minimum when x equals 0. Now, we could also state, if this was a closed interval here, if d was part of our domain, that this would also be a relative minimum, but because it's open, we don't have a relative minimum there. We don't have anything going on there. So those are our relative extrema, or at least that's where they occur. We could also say that the relative maximums are f of a, f of b, and f of c, and the relative minimums are f of 0. Now let's go ahead and talk about global or absolute extrema. Well, for a point to be an absolute extrema, or an absolute maximum, it must be the highest point in the graph, and you can't have an absolute maximum unless it's first a relative maximum. So we know that the absolute maximum have to come from A, B, or C, or there is no absolute maximum. We'll talk about that in a second. But we would say that the absolute maximum is when x equals c. Because at x equals c, that is the highest point on the graph. We also notice that c is, or when x equals c, we have a relative maximum, okay? Now, when we're talking about absolute minimums, well, we only have one relative minimum, one local minimum, and that's when x equals 0. But that doesn't mean it's got to be the absolute minimum just because it's the only relative minimum, okay? Because you can look at the graph and answer the question, is there any points on that graph that are lower than x equals c? And the immediate answer and the obvious answer is yes, there are points that are lower than f of 0 when x equals 0. We can see that all these points within the interval 0 to b are lower than it. And so then you'd say, well, then what is the absolute minimum? Well, we would like to conclude that this is our absolute minimum. The problem with that is that point doesn't exist. So this is a case where we don't have an absolute minimum. It just does not exist. The absolute minimum does not exist. Okay, so that's number 1 for you. So for number 2, it's asking us to take the derivative of natural log of 5 to the 2x. The derivative in respect to x of natural log of 5 to the 2x. So again, keeping in mind that this is an action, this is a verb here. It's telling us to do something here. It's telling us to take the derivative in respect to x of this function. So when I go to take the derivative of this, I'm going to notice that this is the chain rule. It's actually a multiple part chain rule. And it might be nice to see how this breaks down. So what I'm going to do is I'm going to underline the pieces of this chain, or the pieces of this composition. I notice that the outermost function is natural log of something. And then inside of that natural log, we have 5 to the 2x. And then inside the 5 to the 2x, we have 2x as the inner part of the composition. So when we go to take the derivative of this, we take the derivative of the outside thing. So we're going to take the derivative of natural log of something. So the derivative of natural log is 1 over the inside. So 1 over 5 to the 2x. So now we've taken the derivative of natural log. Then multiply that by the derivative of the inside. So we have 5 to the 2x. Well, the derivative of 5 to the 2x is, remember, that's exponential. So the derivative exponential function is the function itself. So it's 5 to the 2x times the natural log of the base. So the natural log of 5 here. So now we've taken the derivative of the exponential function. Now we have to take the derivative of what's inside of that. And so we have to take the derivative of 2x. So times the derivative of 2x is 2. So just so we can see this here, taking the derivative of natural log of something is this component. Taking the derivative of 5 to the 2x is all of this. And then taking the derivative of 2x is this. So that's the chain rule in play there. And from here we can simplify it pretty easily. We notice that the 5 to the 2x's actually cancel out, they reduce, and you're left with natural log of 5 times 2. Or we can write it like this so that we don't mix things up. 2 times natural log of 5. The reason I like it like that is because this could be a little deceiving here. We're actually taking the natural log of just 5, not 5 times 2. So it might be beneficial to put parentheses around this guy. So that's one method in solving that derivative, taking that derivative. That's the long method. If you notice, we have a log, and we can use the power rule with logs. And so we can rewrite this function to be the derivative in respect to x of 2x times the natural log of 5. Okay? So now if I take, that's just using the power rule of a logarithmic function here. So now if I take the derivative of this guy, I have a product of two things. So I want to look at this two different ways. Again, there's two different ways of looking at this. I could take the derivative of each piece here and use the product rule. So I'm going to underline each piece. Well, we have the first piece is 2x, and the second piece is natural log of 5. So remember, the product rule is the derivative of the first thing times the second plus the derivative of the second thing times the first. So the derivative of the first thing is just 2, then times the second thing, so times natural log of 5, plus the derivative of the second thing. Now, here's where students make mistakes. Here's where I see a lot of mistakes when it comes to logarithms and taking derivatives. If I were to plug in natural log of 5 into my calculator, I would get a numeric value. I'd get a number out of it. Natural log of 5 is a constant, you could say. It's a value. There's no variable in that expression. So this is actually a constant. And so the derivative of natural log of 5 is the same as the derivative of a constant, which is 0. And then we'd multiply it by the first thing, which is 2x. Now I want to take a side look at this, because this is what I see students do all the time. The derivative in respect to x of natural log of 5. I see students doing this. They say, well, the derivative of natural log is 1 over something, so 1 over 5. Okay? Now, that's a false thing. That's wrong here because this is a constant. But if you wanted to take the derivative like that, this is, again, the chain rule, if you want to look at it this way. The natural log of something, so the derivative of natural log of something is 1 over the something. And then now we have to take the derivative of the inside thing. Well, the inside thing in this case is 5. So the derivative of 5 is 0. And so really it just cancels out like we saw over here. But you really want to be careful here. If you see the natural log of a number, that is a constant value. And so the derivative of that is 0. And so you can see that these actually end up being the same result. You get 2 times the natural log of 5. Now, an even quicker way of looking at this problem is understanding that when I have natural log of 5, it's a constant, and I can just deal with that using the constant multiple rule. So if I were to take this natural log of 5, it's a constant, and move it out, take it out, I can look at it this way. We have actually the derivative. Let me rephrase that. We can take the constants out. We have natural log of 5 and 2. So that's the same as saying 2 times natural log of 5 times the derivative in respect to x of just x, because the 2 and the natural log of 5 are both constants. Well, the derivative of x is just 1, and then those are constants, so the constant multiple rule says you just take the constant and multiply it by the derivative of whatever leftover you have as a function. So that's pretty simple. That's just 2 times natural log of 5. So there's lots of different ways to find derivatives. You just have to make sure you're using proper mathematics, because we see errors all the time. And you all know what I observe over time, and we all know it to be true, that most of the errors that happen in a calculus class are not calculus problems. The errors happen in algebra and arithmetic. So be careful with that stuff. Make sure you have a good foundation in those things. So anyways, that's the warm-ups for lesson 4.2. We're going to start the lesson on the next video, and we're going to be talking about critical points. Kind of a fun topic, but of course I think everything in calculus is fun. So see you in just a minute.